Imagine standing on the rim of Africa's Great Rift Valley on an afternoon 1.9 million years ago, and the light is turning golden as it stretches across the savannah. The sun hangs low and patient in the sky, casting long shadows from scattered acacia trees, and those shadows are stretching out like the fingers of some enormous gentle hand across the grassland. The air around you is warm and still, carrying the scent of dry earth and distant water sources hidden somewhere in the valleys below. It's a landscape of tremendous distances, where you could see for miles in almost every direction, and the horizon seems to go on forever, melting imperceptibly into the haze where sky and earth become indistinguishable. The grassland itself is a rippling ocean of golden and amber hues, with individual blades catching the light and creating a subtle shimmer across the terrain. Each grass seed head is a tiny universe unto itself, catching and refracting the light in ways that create an almost shimmering quality to the landscape. This is your world, if you were alive then, and this world is about to change not because of any single moment or dramatic event, but because of a species that would walk across it and keep walking, and never truly stop walking until they had crossed continents and oceans and reached the edges of the world. But before that dispersal, before the great journeys across continents begin, let us settle into this moment, into this landscape, and let us simply be present with what we find here. The acacia trees, scattered across the grassland, are not dense enough to be called a forest, nor sparse enough to be called parkland. Rather, they create a kind of savanna woodland, a landscape that offers both shelter and open space, both shade and sunlight, both the cover of branches and the sightline of grass plains. The trees are gnarled and twisted, shaped by millennia of wind and drought and regrowth. Their branches spread wide and flat, creating something like an umbrella overhead, and under these umbrellas, animals gather during the hottest part of the day, seeking relief from the intense equatorial sun. The animals themselves are visible in the distance, moving across the grassland in the way that animals move in wild places, with a kind of purposeful casualness. There are zebras, their white and black stripes creating a dazzling pattern in the afternoon light, making them almost shimmer as they move. There are wildebeest, large and ungainly in appearance, but possessed of a surprising grace in their movements. There are Cape buffalo, massive and imposing, moving with the confidence of dangerous creatures, and there are others, great herds of them, prehistoric animals that have long since vanished from the earth, leaving only bones and fossils to tell their story. The sound of these animals is part of the landscape too. The deep vocalizations of the herbivores, the territorial calls of predators in the distance, the endless chorus of insects that creates a background hum to all of life in this place. The sky above is vast and blue, with only occasional clouds to break the expanse. These clouds are small and white, and they move with the gentle wind that flows across the grassland. That wind carries with it the scent of the African wilderness, the smell of dry earth, the smell of growing things, the smell of water sources located somewhere beyond the visible horizon. And as the afternoon wears on toward evening, the light begins to change. The sun, which was high and bright just hours ago, begins its descent. The light becomes more golden, more amber, more deeply coloured. The shadows of the trees and the larger rocks begin to stretch across the grassland, growing longer and longer as the sun sinks lower in the sky. These shadows create a kind of geography of their own, a pattern of light and dark that would guide travellers across the landscape, that would tell them where shade and shelter could be found. Let me tell you about them as you settle deeper into your rest, as your breathing becomes slower and more natural, as your shoulders begin to release the tension they have been holding. Let me tell you about Homo erectus, the species that stood upright, that walked with the grace of a runner, that looked up at the stars and wondered what lay beyond the horizon. They were not like the earlier humans who had come before them. They were taller, stronger, faster, and their brains had grown in ways that would reshape the very landscape of human possibility. And what's remarkable about what we know of them comes from fragments of bone and stone scattered across 3 continents, pieces that archaeologists have painstakingly gathered and studied, trying to understand the story of this incredible journey. 2 million years is an almost unimaginable span of time. To put it in perspective, modern humans, you and me, people like us, have existed for only about 300,000 years. We have built civilizations for only about 5,000 years. We have had writing for only about 5,000 years. We have had electricity for about 150 years. The entire span of recorded human history, Everything that has been written down and preserved, everything from ancient Egypt to the fall of Rome to the rise of nations and the spread of religions, all of that is just a tiny fraction of a percent of the time that Homo erectus existed on this earth. If you imagine the entire history of Homo erectus as a single day from sunrise to sunset, then all of recorded human history would be just a few seconds at the very end of that day, after the sun was already below the horizon and darkness had begun to fall. Yet during those nearly 2 million years, Homo erectus was doing something that no earlier human species had done. They were spreading. They were moving out of Africa, the continent where their species had originated, and they were establishing themselves in new places, in new climates, under new stars. They were adapting to environments that their ancestors had never experienced. They were developing new tools, new technologies, new ways of understanding and manipulating the world around them. They were, in short, becoming something new, something that would eventually lead, through a long chain of evolution and adaptation and change, to you and me, sitting here in the darkness, listening to stories of ancient peoples who walked the earth so long ago that we cannot even properly comprehend the time span involved. One of the most complete stories we have about what these people looked like comes from a young individual discovered in 1984 near Lake Turkana in Kenya. His name has become legendary in the field of paleoanthropology, though he never knew that name while he was alive. His catalogue number is KNM-WT15000, but the world knows him as Turkana Boy. He was discovered by a man named Kamoya Kimeu, a renowned fossil hunter who had spent decades searching the arid badlands around Lake Turkana, turning over rocks and scanning the eroded hillsides with the patience and attention that only comes from deep practice and genuine love for the work. Kimeu was a Kenyan fossil hunter of legendary skill and dedication. He had spent his entire career in those badlands, and he knew them the way a farmer knows his fields, the way a bird knows the territory where it roosts. He could read the landscape in ways that most people cannot. He could look at an exposed cliff face and see, in the patterns of the rocks and the strata, the history of ages. He could walk across a desert floor and spot, among millions of stones, the one that was different, the one that bore the signature of bone. When Kimeu found those first fragments of bone in 1984, he recognized immediately that he was looking at something extraordinary, something that would capture the world's attention and help us understand our own ancestry in new and profound ways. The bones were not scattered randomly, as bones often are in the fossil record. Instead, they were relatively complete and relatively well preserved. Kimeu called in the other researchers, and the site was carefully excavated. As the work continued, more and more bones emerged from the sediment. Femurs, ribs, vertebrae, finger bones, toe bones. Piece by piece, the skeleton of a young individual came into view. In total, 108 distinct bones would be recovered, making this the most complete Homo erectus skeleton ever found. It was a moment of tremendous significance for the field of paleoanthropology, a moment that would generate new insights and new questions about who Homo erectus was and how they lived. Turkana Boy was only 8 or 9 years old when he died. Even though he had not yet reached adulthood, his skeleton tells us remarkable things about his species. His bones are nearly complete, and from careful analysis of his remains, we can calculate that he was already approximately 1.6 meters tall. That is about 5 feet 3 inches. This meant that had he lived to adulthood, he would have stood taller still, perhaps reaching 1.75 or even 1.8 meters, or nearly 6 feet. For reference, the average height of modern humans is around 1.75 meters for men and 1.62 meters for women. So Turkana Boy's species, Homo erectus, was reaching modern human heights, or even perhaps slightly exceeding them. He weighed around 48 kilograms, about 106 pounds, at the time of his death, and his body was already showing the characteristic proportions of his species. Those proportions are crucial to understanding what Homo erectus was becoming. His limbs were long, not just absolutely long in terms of centimeters, but long relative to his torso. This is the opposite of his earlier ancestors, creatures like Homo habilis, who had relatively short legs and long arms, a body proportion that reflected their partially arboreal heritage, their connection to life in trees. But Homo erectus was different. In Homo erectus, the legs were becoming the dominant feature. The legs were long and relatively thin, suggesting not raw muscular power but rather efficiency and endurance. The leg bones show the kind of development that comes from bipedal running, thick and robust, designed to absorb impact, but streamlined rather than bulky. The feet were arched, creating a springy mechanism. The arms were shorter relative to the body than in earlier hominins, and the hands were becoming more delicate, more capable of fine manipulation. This was the body of a creature built for striding across open ground, for moving across distances, for running. But there is something else that Turkana Boy's skeleton reveals. He had a spinal condition, perhaps a degenerative disease that would have caused him pain throughout his life. The vertebrae show signs of deformation, of changes that would have made movement difficult and uncomfortable. His growth was disrupted by illness. His life, even at the age of 8 or 9, had not been easy. Yet despite this condition, despite the pain and the limitation it would have imposed, Turkana Boy survived. His bones show no signs of malnutrition or starvation. His condition did not kill him instantly. Something else eventually killed him. Perhaps an infection, perhaps an accident, perhaps simply the accumulated stress of living with a chronic condition in a harsh environment. But the fact that he survived at all with this condition tells us something important about his species. They cared for their young. They tolerated weakness among their group. They did not abandon individuals simply because those individuals could not keep pace with the group's movement and hunting activities. Picture Turkana Boy at age 8 or 9. His mother is still alive, or perhaps she died in childbirth with his younger sibling and another individual, another woman or perhaps a female relative that has taken him under her care. His back hurts. It hurts constantly, a dull ache that sometimes flares into sharp pain when he moves certain ways. He cannot run as fast as the other children. He cannot keep up with the group when they move from one location to another. Yet they do not leave him behind. Somehow, despite the burden he represents, despite the way his condition slows the group, they continue to care for him. Someone brings him food, probably food that is carefully prepared, food that is easy to chew and digest because his condition makes vigorous chewing difficult. Someone makes sure he stays close to the fire at night, where he is warm and safe. Someone touches his back gently, perhaps sensing his pain and seeking to provide comfort. This kind of care, this kind of compassion, is what the skeleton of Turkana Boy reveals. It reveals a species that was capable of recognizing suffering in others, capable of responding to that suffering, capable of extending extraordinary effort to sustain a young individual who, from a purely practical standpoint, might have been seen as a burden. This image of Turkana Boy, this young individual with his elongated limbs and his growing brain, gives us a window into what the species as a whole was becoming. Homo erectus was not like Homo habilis, the earlier species that had preceded them by perhaps 1 million years. Habilis was smaller, more ape-like in many ways, with shorter legs and less sophisticated tools and a brain that had not yet undergone the remarkable expansion that Erectus would experience. The brain of Homo habilis was typically in the range of 600 to 700 cubic centimeters, about the size of a modern chimpanzee's brain. Habilis had a brain that was somewhat enlarged compared to Australopithecines, but it was not dramatically enlarged. The body of Habilis was also smaller and more ape-like, with shorter legs and longer arms, suggesting that these individuals were still spending some time in trees, still maintaining some of the bodily characteristics of their arboreal ancestors. But Erectus was different. Erectus was becoming something new, something that would spread across the world and leave its mark on every continent except Antarctica, something that would persist for nearly 2 million years, far longer than our own species has existed so far. Homo erectus brains range from about 700 cubic centimeters in the earliest forms to nearly 1,200 cubic centimeters in the latest forms. This is a remarkable expansion, an enormous growth in neural tissue that represents a fundamental reorganization of the human mind and its capabilities. The body of Erectus was fully adapted for bipedalism. The legs were long and built for striding. The arms were shorter, no longer equipped with the curved fingers suitable for grasping branches. These individuals were terrestrial creatures, committed to life on the ground, using their intelligence and their tools to survive in an environment that was increasingly open grassland rather than dense forest. Now, when we think about Homo erectus, we must recognize that the species was not static. Over the nearly 2 million years of their existence, they changed, evolved, developed new capabilities, refined their tools, and adapted to new environments. The process of evolution, when viewed over such vast timescales, can appear almost impossibly complex. Small changes accumulate. Populations diverge. Some lineages thrive while others fade away. Different populations in different locations experience different selective pressures, and those pressures shape the populations in different ways. Recent discoveries have shown us just how complex this emergence was, how multifaceted and multifarious the process of human evolution actually is. In December 2025, researchers published groundbreaking findings about a remarkable fossil discovered at a site called Gona in Ethiopia. Gona is located in the Awash River Valley, a region that has yielded numerous important hominid fossils over the decades. The fossil in question, catalogued as DAN5, is a complete early Pleistocene cranium, that is, a complete skull, the first of its kind recovered from the Horn of Africa, and it dates to between 1.5 and 1.6 million years ago. This means that Dan5 is roughly contemporary with Turkana Boy, or perhaps slightly older. What makes DAN5 so extraordinarily remarkable is that it is what researchers call a mosaic fossil, containing features from multiple evolutionary trajectories. In other words, it has some characteristics that appear modern or progressive, while simultaneously having characteristics that appear ancient or archaic. The cranium itself, the brain case, has characteristics similar to Homo erectus. The overall shape and structure is consistent with what we know of Erectus, but the face, the facial structure, and the brain structure show features more similar to basal Homo types that came before Erectus. The brain volume of Dan5 is 598 cubic centimeters, which is actually quite small for Erectus. This is smaller than the average Erectus brain, and it is in the range of the larger-brained Homo habilis individuals. The combination of a relatively small brain with Erectus-like cranial features suggests something remarkable, that the emergence of Homo erectus was not a simple linear transition from one form to another, a moment where habilis gradually became Erectus, and the story was complete. Rather, it was a complex, multifaceted process involving multiple populations and directions of evolution simultaneously. This mosaic quality of DAN5 is deeply important for us to understand as we contemplate the story of Homo erectus. The individuals we call Homo erectus were not identical beings across space and time. They were not a single, unchanging species, fixed and stable. Rather, they were populations that varied, that adapted locally, that maintained certain features while developing others, that sometimes moved in different evolutionary directions simultaneously. The species was in conversation, so to speak, with its own evolutionary possibilities, exploring different pathways, different strategies for survival and reproduction in different environments. In the Rift Valley of Kenya, we see Turkana Boy, tall, long-legged, fully terrestrial. In Ethiopia at Gona, we see DAN5, smaller-brained, showing features of earlier forms, yet with some emerging characteristics of the newer Erectus type. These are not inconsistencies or contradictions. Rather, they are windows into a process of evolution that was far more complex and multifaceted than we often acknowledge. The DAN5 fossil is also significant for another reason. It represents the first known individual of Homo erectus to produce both Oldowan tools, the earlier, simpler chopper and scraper technology that had been used by Homo habilis, and Acheulean hand axes, the more sophisticated technology that would become characteristic of Erectus. This suggests that in one individual, in one population, we are seeing the transition between two different tool-making traditions. The individual or population represented by DAN5 was capable of making both the earlier and the newer tool types. Over time, the newer Acheulean technology would become dominant, would spread, would become the characteristic toolkit of Homo erectus. But at this moment in time, captured in the fossil record, we see both traditions coexisting. Imagine standing with DAN5, or with one of their relatives from the same population. You're in Ethiopia, in the Rift Valley, at the edge of a seasonal river. The individual before you is smaller-brained than later Erectus, but they have the long legs and upright posture that marks them as fully committed to bipedal existence. In their hand, they hold a stone tool. Is it an Oldowan chopper? Is it an Acheulean hand axe? Perhaps it is something in between, a tool that is transitioning from one tradition to the other, carrying characteristics of both. The individual has the knowledge to make both types of tools. They understand the different techniques, the different strike angles, the different purposes for which each tool is used. In their mind, in their knowledge, the tradition is changing. What was standard a few thousand years ago is beginning to give way to something new. A younger generation, perhaps, learned the new technique from their elders, and they are now passing it on. The old knowledge is not lost, and for a while both are used, but gradually, the new is replacing the old. Let your mind settle now as you contemplate these ancient people, these early members of the human family who walked beneath the same stars that you can see in the night sky, who felt the warmth of the sun on their skin, who experienced hunger and thirst, and the joy of a successful hunt. They were not so different from you in their basic needs and desires. Though their world was vastly different, their knowledge was vastly different. Their capabilities and limitations set them apart in important ways. But they had hope. They had curiosity. They had the capacity to wonder about what lay beyond the next valley, the next river, the next mountain range. And increasingly, they had the physical and mental tools to do something about those wanderings. They had legs that could carry them vast distances, and they had brains that were growing larger and more capable with each generation. The body of Homo erectus was engineered, so to speak, for movement. If you could examine one of them closely, if you could look at the proportions and the musculature and the bone structure, you would see a being designed by millions of years of evolution to cover distance. Every aspect of their anatomy was shaped by selection pressures that favoured mobility, endurance, and the capacity to traverse vast landscapes. The long legs that we see in Turkana Boy, and that we can infer from other skeletal remains scattered across 3 continents, made Homo erectus the first truly effective runner among the hominins. They were not the strongest, not the most aggressive, not the best sprinters in absolute terms. Rather, they were the best at something different. They were the best at going far. They had what we might call an athlete's build, lean, muscular, with the kind of frame that is optimized for endurance rather than raw strength. The legs were particularly long relative to the arms and torso, a proportion that is excellent for forward motion, for striding across open grassland, for pursuing prey animals for hours and hours until those animals became so exhausted that they could be harvested for food. Let me describe the specific anatomical features that made this possible. First, consider the length of the lower limb relative to the upper limb. In modern humans, the lower limb accounts for about 55% of our total body height. In our ape cousins, the proportion is more like 45%. They have relatively longer arms and shorter legs, but in Homo erectus, and we can see this clearly in Turkana Boy, the legs were nearly 55% of body height, approaching modern human proportions. The femur, the thigh bone, was long and relatively straight. Unlike Australopithecines, where the femur sometimes had a more pronounced curve, the erectus femur was nearly straight, which means that the weight was carried directly over the feet, making walking and running much more efficient. The tibia and fibula, the bones of the lower leg, were also long and built to be strong. These are the bones that bear the weight of impact with every footfall. When you run, there is a moment of impact where your entire body weight, multiplied by the force of that impact, comes down on those bones. They need to be thick enough, robust enough to handle that impact repeatedly, step after step, hour after hour. The bones of Homo erectus show this robustness. They are not delicate or thin. They are built like the legs of a creature that spends significant time in motion. Then there is the architecture of the foot. In modern humans, the foot is an engineering marvel. It has an arch, a natural curve from the ball of the foot to the heel that acts like a spring. This arch allows the foot to absorb impact, to store energy, and to return that energy with the next step. It allows us to run more efficiently, to cover distance more easily, to maintain a steady pace for hours. In Homo erectus, the foot was similar to the modern human foot. The arch was pronounced. The big toe was aligned with the other toes, not splayed to the side as in apes. The overall structure of the foot was that of a creature built for terrestrial running. And then there is the Achilles tendon, that thick cord at the back of the ankle that connects the calf muscle to the heel bone. In Homo erectus, this tendon was long and powerful. When you push off the ground while running, the calf muscle contracts, and that contraction is transmitted to the heel bone through the Achilles tendon, lifting your heel and propelling you forward. A long, powerful Achilles tendon allows for more efficient push-off, more energy transfer, more efficient movement. The soleus and gastrocnemius muscles, the calf muscles that power the Achilles tendon, were likely large and powerful in Homo erectus. When these muscles are used repeatedly over hours and hours of running, they become very efficient at generating the forces necessary for forward propulsion. All of these features, the long legs, the straight femur, the robust leg bones, the arched foot, the powerful Achilles tendon, the strong calf muscles, work together to create a creature that is supremely adapted for covering distance, for sustained running, for the kind of endurance activity that would allow a hunter to pursue prey for many hours. This is not a body built for climbing trees or for wrestling opponents or for raw strength. This is a body built specifically for one thing: going far, going for a long time, covering ground that our ancestors would not have thought possible. This brings us to one of the most fascinating aspects of Homo erectus' existence: persistence hunting. This is a hunting strategy that depends on the unique physiological capabilities of human beings, capabilities that Homo erectus had begun to develop and perfect. Unlike most predators, which depend on short bursts of speed to catch their prey, persistence hunters depend on the ability to maintain a steady pace for extended periods, gradually wearing down prey animals until those animals can no longer flee. Humans are among the best endurance runners in the animal kingdom, and this capability emerges from a particular set of physiological features that Homo erectus possessed to a remarkable degree. Consider the cooling system. Your body and the bodies of Homo erectus are covered in sweat glands, billions of them, scattered across nearly every surface of your skin. These are called eccrine sweat glands, and they represent a major evolutionary innovation. Most mammals cool themselves by panting, or by seeking shade, or by reducing their activity during the hottest parts of the day. But humans, and Homo erectus in particular, have evolved an entirely different strategy. We cover our bodies in sweat-producing glands that can evaporate moisture and release heat at a rate that allows us to remain active in conditions that would cause other animals to overheat and die. This is an incredible advantage in the African savanna, where temperatures can soar and where the sun beats down relentlessly for hours and hours. Homo erectus, with their large body size and their extensive coverage of eccrine sweat glands, could do something that earlier hominins could not do as effectively. They could pursue prey animals in the middle of the day under the full heat of the sun in conditions that would cause other predators to seek shelter. A lion, or a hyena, panting heavily, losing its pace as its body temperature rises, cannot maintain its pursuit indefinitely. But a Homo erectus hunter covered in sweat, evaporating moisture efficiently, could continue, steadily, relentlessly, mile after mile. The prey animal, whether it was a wildebeest or a zebra or a buffalo, would eventually reach its thermal limit. The animal would begin to slow, it would become disoriented, its body temperature would rise uncontrollably, and at that point, the human hunters, still moving with purpose and determination, would be able to move in and secure their meal. The anatomy supporting this capability is remarkable in its precision. The Achilles tendon, that thick cord at the back of the ankle, is particularly long and powerful in Homo erectus. This tendon transfers force from the calf muscles to the heel bone, and its length and strength allow for efficient striding. The arch of the foot is pronounced, creating a natural spring-like mechanism that returns energy with each step. The legs are long relative to the torso, which means each stride covers more ground. The center of mass is positioned in such a way that the energy cost of running is minimized. All of these features, taken together, create a creature that is supremely adapted for the long-distance pursuit of prey. But there is a limit to this endurance, and it is an important limit to understand. The human body, no matter how efficient it is at cooling through sweat, will eventually reach a point of dehydration where it cannot continue. Research has suggested that under ideal conditions, with access to water and with moderate activity, a Homo erectus individual might be able to maintain a pursuit hunt for somewhere between 5.5 and 5.7 hours before reaching their absolute physiological limit, before their body simply could not continue. This is a remarkable period of time, far longer than most animals could sustain pursuit, but it is not infinite. It means that the hunt had to be timed and planned carefully. It had to begin when there was enough daylight remaining, or when the prey animal was in a vulnerable location. The hunters had to understand the landscape, the water sources, the typical patterns of the prey animals. This was not mindless running. This was intelligent, planned hunting, based on observation and experience and accumulated knowledge passed from one generation to the next. Imagine now what it would have felt like to be one of these hunters, moving steadily across the savannah in the early morning hours, when the sun is still low and the temperature is still manageable. Your legs are moving in that easy, efficient stride that your species has perfected over hundreds of thousands of years. Your breathing is steady and controlled. Your mind is focused on the prey animal ahead, on its movements and its apparent condition. You're not alone. There are others with you, perhaps 4 or 5 of you, all moving in coordination, perhaps taking turns at the front to split the wind resistance. The hunt begins in darkness, or in the pre-dawn twilight. The group has spotted the prey animal the evening before or perhaps early this morning. It is a wildebeest, a large herbivore perhaps twice your body weight, moving through the landscape seeking grass and water. The hunters have positioned themselves carefully, reading the wind, understanding where the animal is likely to move. As the sun begins to rise, the hunt begins. The lead hunter starts the pursuit, moving toward the prey animal. The animal sees the hunter and flees. This is what the hunters want. They are not trying to sneak up on the prey. They are trying to trigger the flight response to activate the animal's panic and desperation. The wildebeest runs, and the hunters follow, maintaining a steady pace. This is not a sprint. This is a marathon. The lead hunter drops back after a few kilometers, and another hunter takes the front position. The pace is maintained, steady, and relentless. The wildebeest is faster than the hunters in short bursts, but the hunters can maintain their pace for hours. Hours pass. The sun rises higher. The temperature increases. You feel the heat now, but your body is dealing with it well. The sweat is flowing freely. Your eccrine glands working at maximum capacity, evaporating moisture and cooling your body. Your breathing remains controlled. Your legs continue their rhythmic stride. The wildebeest, meanwhile, is beginning to struggle. It has already run hard in short bursts multiple times. It is not adapted for sustained running in heat. Its body temperature is rising. It cannot sweat the way humans can. It is beginning to overheat. Its gait becomes less coordinated. It makes poor decisions, running in directions that do not lead to safety. The hunters continue, steady, relentless. By mid-afternoon, several hours into the hunt, the animal is showing clear signs of distress. It is slowing. It is stumbling occasionally. It is disoriented. The hunters sense the kill is near. They maintain their pace but prepare themselves. The lead hunter may be carrying a wooden spear, fire-hardened at the tip, or perhaps just a sharpened stick. Or perhaps the hunters rely on throwing stones or on running the animal until it literally cannot move, then dispatching it with whatever weapons and tools they have at hand. Different groups in different times might have used different techniques, but the principle is the same. Wear down the prey until it cannot resist, then harvest the meat. When the moment comes, when the wildebeest can no longer flee or fight, the kill is achieved. The hunters process the carcass with their hand axes, cutting through hide and muscle, breaking open bones to access the bone marrow. The meat is divided. Some will be eaten immediately, some will be dried for later consumption. The hunters have food for days, perhaps weeks. The successful hunt means survival. It means health and strength. It means the ability to support the group, to care for the young and the old and the disabled. Hours pass. Now this kind of hunting, this persistence hunting, would have provided Homo erectus with a reliable source of meat, a source that was more dependable than the scavenging that earlier hominins had relied upon. And meat, as we will discuss, was crucial to the development of Homo erectus. But there is another aspect of sleep and rest that is also crucial to our understanding of Homo erectus, and that is the fact that these behaviours, this running, this hunting, would have dramatically changed the sleep patterns of the species. Think about sleep in the context of evolution. Most primates, our closest living relatives, the apes, spend a significant portion of their day sleeping. A chimpanzee might sleep 12 hours or more per day, often in multiple bouts, sleeping in trees at night and sometimes resting during the heat of the day. But as our ancestors came down from the trees and began to spend more time on the ground, the pattern of sleep had to change. Ground sleeping is more dangerous than tree sleeping. A sleeping animal on the ground is vulnerable to predators, so humans developed a different strategy. Rather than sleeping long, distributed periods throughout the day and night, humans began to compress their sleep into fewer, more intense bouts. We sleep primarily at night, and we tend to sleep in one main consolidated period, though we also have some capacity for short naps during the day. But there is something else that changed as well. The character of human sleep itself became different. Humans, uniquely among primates, have a very compressed sleep schedule combined with a very high sleep intensity. We spend a higher proportion of our sleep time in rapid eye movement sleep, or REM sleep, than do other primates. REM sleep is when most of our dreams occur, and it is a time of intense brain activity. Other primates tend to have long, slow sleep periods with less REM density. But humans, and this may have begun with Homo erectus, as they moved to ground sleeping and developed the hunting behaviors we have been discussing, humans have what researchers call intense sleep. We sleep less than other primates, but we sleep more deeply, with higher REM density and higher overall sleep intensity. This change may have been necessary as humans became ground sleepers. By developing more intense sleep, we could consolidate our sleep into fewer, shorter periods, reducing our vulnerability while still getting adequate rest. Sampson and Nunn, researchers who study the evolution of sleep, have proposed that this shift toward compressed, intense sleep may have begun as early as the Australopithecines, but it likely intensified with Homo erectus as they became increasingly terrestrial, increasingly committed to ground sleeping rather than tree sleeping. The shift would have been gradual, taking place over thousands of generations, but it would have been profound in its effects. As Homo erectus developed this compressed sleep schedule, they would have had more time awake, more time to perform other activities, more time to travel and explore and hunt. The trade-off was that their sleep would have to be more efficient, more intense, more capable of fully restoring the body and mind in a shorter period of time. This is the beginning of something that would ultimately lead to humans as we know ourselves today. We are creatures of intense compressed sleep. We are creatures of long-distance movement. We are creatures whose brains have expanded far beyond what they were in our earliest ancestors. And all of these features began to develop, began to accumulate during the time of Homo erectus. As you lie here, as your own sleep deepens and your mind becomes less focused on the details of the world around you, as you perhaps begin to drift toward that twilight state between waking and sleeping, know that you are experiencing something that your ancient ancestors also experienced, something that has been shaped by millions of years of evolution, something that connects you across an almost unimaginable span of time to those people who walked beneath African stars and wondered about the world beyond the horizon. The physical capabilities of Homo erectus, the long legs, the efficient cooling system, the capacity for endurance running, all of these were necessary but not sufficient for the great dispersal that would come. For Homo erectus to successfully move out of Africa and into new continents, they needed tools. They needed not just the basic choppers and scrapers that Homo habilis had made, but something more sophisticated, something that spoke to a growing capacity for abstraction and planning and forward thinking. They needed the hand axe. The Acheulean hand axe, named after the French town of Amiens, Amiens in an ancient form was called Amiensian, represents a major leap forward in tool technology. These are not the crude, sharp-edged rocks that served as the basic tools of Homo habilis. The Acheulean hand axe is a thing of beauty, of apparent purposefulness, of craftsmanship. They are typically teardrop-shaped, with a pointed end and a blunted base, and they are remarkably symmetrical. This symmetry is striking when you hold one in your hands or when you see photographs of them. The two sides of the axe are nearly mirror images of each other. The edges flow smoothly from the point to the base. The tool shows evidence of careful planning and execution. The appearance of the Acheulean hand axe in the fossil record coincides roughly with the appearance of Homo erectus, beginning around 1.7 million years ago. What is remarkable is that this tool type persists for an extraordinarily long time. At a site in Kenya called Ologosaili, archaeologists have found a remarkable concentration of hand axes, spanning from roughly 1.2 million years ago to perhaps 500,000 years ago. Imagine walking across the landscape of Ologosaili during this period and seeing hand axes everywhere, not scattered randomly, but in concentrations, in what archaeologists call hand axe fields, suggesting repeated occupation of the same location, repeated manufacturing of these tools over vast stretches of time. The stones used were carefully selected, often with colours and textures that made them suitable for flaking and shaping. The tools themselves show no signs of having been used extensively. Some are so beautifully made that they seem almost too perfect to use, suggesting that perhaps their manufacture itself, the process of making them, was important. This brings us to an interesting and ongoing debate among researchers who study Homo erectus. The symmetry of the hand axe has led some scientists to propose that the creation of these tools requires a level of language development and abstract thinking. The argument is as follows. The hand axe is symmetrical, and the symmetry serves no obvious functional purpose. A hand axe would work just as well asymmetrically. In fact, asymmetrical tools would be easier to make. You would not have to put in the extra effort required to achieve symmetry. Therefore, the creation of the symmetrical hand axe suggests that the maker had some abstract concept in mind, some ideal form that they were trying to achieve, and the transfer of this ideal form from mind to stone, the ability to envision the tool before making it, to correct and refine it as it is being made, to achieve symmetry. This may require language. It may require the ability to communicate about abstract concepts. The symmetry of the Acheulean hand axe is not random or accidental. It appears to be intentional. The maker deliberately crafted both sides of the tool to match each other. This is particularly apparent when you examine the edges. The edges should flow smoothly from the pointed end to the blunted base. If you laid a hand axe flat and drew a line down the center from point to base, the edge on one side would be a mirror image of the edge on the other side. This level of precision requires not just skill, but also planning and intention. The maker has an image in their mind of what the tool should look like, and they are actively working to achieve that image through the process of napping. Different researchers have proposed different explanations for the symmetry. Some believe it is purely functional, that the symmetrical hand axe is actually more efficient at cutting and butchering than an asymmetrical tool. Others believe it is symbolic, that symmetry was valued for its beauty or its representation of some concept important to the culture. Still others believe it is a byproduct of learning and practice, that individuals who made hand axes repeatedly, practicing the technique over and over again, developed hands and brains that naturally produce symmetrical forms. What is clear is that the brain regions involved in tool-making are the same brain regions involved in language production and the control of fine motor skills in the hands and mouth. The primary motor cortex, the part of the brain that controls voluntary movement, is organized in a specific way. Different regions of the motor cortex control different parts of the body. A disproportionately large part of the motor cortex is devoted to controlling the hands, particularly the fingers. Another disproportionately large part controls the mouth and throat, the muscles involved in speech. When Homo erectus individuals spent hours making hand axes, napping stone with precision and control, they were exercising these motor cortex regions repeatedly. The neural pathways involved in controlling the hands were being strengthened, were being built up through repeated use. Neuroscience research on modern humans shows that practicing fine motor skills can actually increase the size of the motor cortex regions dedicated to those skills. Musicians who play instruments show enlargement of the motor cortex regions controlling their hands. People who are expert at particular hand tasks, surgeons, craftspeople, show similar enlargement. The neural tissue literally grows and becomes more densely packed with connections when it is used intensively. So when Homo erectus individuals practiced tool-making hour after hour, day after day, year after year, they were not just making tools, they were physically building and strengthening the neural architecture of their brains. And this building and strengthening of the hand control regions may have had a secondary effect on the brain regions devoted to speech. The motor cortex regions for hands and speech are located near each other in the brain, and there are many neural connections between them. As the hand control regions grew stronger and more capable, perhaps the nearby speech regions also benefited from the neural activity. Perhaps the ability to control the fine movements of the mouth and throat to produce the subtle variations of sound that constitute language was enhanced by the same neural processes that were being driven by tool-making practice. In this way, tool-making and language may have co-evolved, each driving the development of the other, creating a feedback loop that led to increasingly sophisticated capabilities in both domains. Moreover, the part of the brain that controls the fine motor skills required for napping, the controlled striking and shaping of stone, overlaps significantly with the brain regions involved in speech and language processing. The development of sophisticated tool-making may have literally built, through practice and use, the neural infrastructure for language. When a Homo erectus individual spent hours and hours making hand axes, napping stone with precision, controlling each strike with exactitude, they were not just making tools. They were building the brain regions that would eventually support language and abstract communication. This was not a one-way relationship, though. The development of language as the brain regions expanded would have enabled the transmission of tool-making knowledge in more sophisticated and detailed ways. A person could now explain, with words, the techniques involved in creating a hand axe. The knowledge could be preserved and transmitted with greater fidelity across generations. The DAN5 fossil we discussed earlier is particularly relevant here. DAN5 is identified as the first known individual of Homo erectus to produce both Oldowan tools, the earlier simpler chopper and scraper technology, and Acheulean hand axes. This mosaic individual, showing both ancestral and derived features, represents the transition point, the moment in evolutionary time when the species was beginning to make this leap in tool sophistication. It was a gradual transition, happening over hundreds of thousands of years, but we can identify the moment when it was occurring, and DAN5 represents one point along that continuum. Let these images settle into your mind gently as your breathing deepens. Picture a Homo erectus individual, perhaps similar to our earlier description of an adult female, sitting on a hillside or near a river with suitable stones scattered nearby. She has found a hammerstone, a rock that is heavy and rounded that will serve as the striking tool. She has also found a nodule of stone, perhaps flint or basalt, that has the right texture for flaking. She turns the nodule in her hands, feeling its weight and balance. She strikes it with the hammerstone at a precise angle, and a flake comes away, revealing a sharp edge. She examines this flake. Perhaps she uses it, or perhaps she sets it aside and continues working the original nodule, striking it again and again, each strike removing a flake, each removal getting her closer to some image in her mind of what the finished tool should look like. Hours might pass. The sun moves across the sky. Other individuals might come and go, or she might work in companionable silence near others who are also working stone. There is an efficiency to the motion, a rhythm that comes from endless practice. Each strike is deliberate, purposeful, guided by an understanding of how stone fractures and flakes. Slowly, very slowly, the teardrop shape emerges, the symmetry develops. The base becomes blunt and rounded, suitable for gripping in the palm, while the point becomes sharp and capable of piercing flesh. When it's finished, it is placed aside, and perhaps the process begins again with another stone. We do not know exactly what Homo erectus did with these hand axes. The most obvious answer is that they used them for butchering, for cutting through hide and muscle to access the meat of large animals. Hand axes appear at sites where the remains of large animals are also found, suggesting butchering. But some hand axes show no evidence of use. Some are so perfectly made that they seem precious in some way. Some sites have concentrations of hand axes with no associated animal remains. It is possible that the making of hand axes was important in other ways, as a social practice, as a way of gaining status or demonstrating skill, as a way of spending time during non-hunting seasons. The truth is that we cannot fully know, but we can recognize that something important was happening here, that Homo erectus was becoming capable of creating complex objects, of executing a plan, of transforming raw stone into a tool of purpose and precision. And this capability, this growing sophistication of mind and hand, would be crucial as Homo erectus faced the next major challenge of their existence, the mastery of fire. Imagine the world becoming darker as the sun sets. As evening comes on, most animals retreat to safer places, into trees, into burrows, into crevices in rock. But early humans, increasingly terrestrial, increasingly committed to ground dwelling, faced the night without adequate shelter from predators. Fire would change everything. Fire would make the night safer. Fire would make food more digestible and more available. Fire would allow for social gathering and the transmission of culture in new ways. Fire would, in short, remake the world that Homo erectus inhabited. The evidence for fire use by Homo erectus is scattered but compelling. The earliest secure evidence of deliberate fire use comes from a site called Wonderwork Cave in South Africa, where archaeologists have found burned bone and ash deposits dating to approximately 1 million years ago. The burning is not the kind of damage that might result from wildfires sweeping through the area. The pattern of burned and unburned remains suggests intentional use of fire, perhaps for cooking, or perhaps for warmth and protection. Around the burned remains, tools were found, suggesting that the fire was being used by the inhabitants of the cave. Later, there is even more direct evidence of fire use combined with food preparation. At a site called Gesher Benot Ya'aqov in Israel, dating to approximately 780,000 years ago, archaeologists made an extraordinary discovery. The remains of fish, over 40,000 individual fish remains, primarily of carp-like species. What makes this discovery so remarkable is that careful analysis using X-ray diffraction has shown that these fish were heated. The heating occurred at temperatures below 500 degrees Celsius, which is consistent with cooking. The fish were not burned by accident, they were prepared, heated deliberately and consumed. This is the oldest known evidence of cooked food in the human record, a moment when someone, somewhere, decided to place a fish in fire or in heated coals, and discovered that the flesh became softer, more palatable, easier to digest. Richard Wrangham, a primatologist and human evolutionary biologist at Harvard University, has proposed a revolutionary theory about the importance of cooking to human evolution. In his book, Catching Fire: How Cooking Made Us Human, published in 2009, Wrangham argues that the control of fire and the development of cooking were not merely incidental to human evolution, they were central to it. He proposes that cooking allowed humans to extract more energy and nutrients from their food, and that this dietary shift was essential for the enormous expansion of the human brain that occurred during the Pleistocene. Consider the mathematics of eating raw food. The human gastrointestinal system is relatively small compared to that of other primates. We can fit a lot of food into our stomach, but our intestines are not as long or as complex as those of our nearest living relatives. When we try to digest raw plant material, our bodies have to work very hard. Wrangham calculated that if a modern human tried to survive on a diet of raw plants, she would have to spend approximately 5.7 to 6.2 hours per day chewing and processing food, roughly 12 pounds of raw plants per day, just to extract enough calories to sustain herself. That is an enormous amount of time. It leaves little time for anything else, for making tools, for hunting, for travelling, for socialising. But cooking changes everything. When food is cooked, the proteins are denatured and become easier for our digestive enzymes to break down. The cell walls of plants are softened and broken down by heat, making the nutrients inside more accessible. Cooking also kills bacteria and parasites that might otherwise make us ill. The result is that cooked food yields more calories and nutrients with less time spent in digestion and processing. A person eating cooked food can satisfy their nutritional needs in far less time, leaving hours for other activities. Wrangham argues that this shift toward cooking, initially involving animal meat since meat appears in the diet of Homo erectus earlier than systematic plant cooking, would have allowed Homo erectus individuals to eat in a shorter time and spend the energy saved on other activities. One of the most energy-intensive activities is the development and maintenance of a large brain. The human brain, even at the size it had reached by the time of Homo erectus, uses approximately 20% of the body's energy budget despite being only 2% of body weight. A larger brain requires more energy. Cooking made this energy available, and as brains grew larger, they became capable of more sophisticated thought, more complex social organization, more abstract reasoning. This, in turn, may have led to more sophisticated cooking, using fire not just to warm meat but to prepare elaborate meals, to preserve food for later, to create new culinary combinations. This is a feedback loop, a spiral of increasing complexity and sophistication. The comfort and the warmth of fire, the gathering of people around it in the evening hours, the safety it provided from night-active predators, all of these would have changed Homo erectus' existence in profound ways. The night would no longer have been a time of retreat and vulnerability. The night would have become a time of social gathering, of conversation, of the transmission of stories and knowledge. The boundary between night and day, between the time of activity and the time of rest, would have begun to shift. Where once Homo erectus would have needed to rest through much of the night, huddled together for warmth and protection, now there was light and warmth available. The night could be a time of activity, of work, of social bonding, of cultural practice. Yet sleep would still come, drawn on by the circadian rhythms of the body, by the body's biological need for rest and restoration. Picture the scene now. It is evening in a cave or rock shelter in the early Middle Pleistocene, perhaps 1 million years ago, perhaps earlier. A fire is burning near the opening of the shelter, tended carefully by individuals who understand its needs and its dangers. The flames are visible for some distance into the darkness beyond the shelter. Inside the shelter, further back from the fire, the air is warm and the light is flickering and uncertain. People are gathered here, perhaps a group of 15 to 25 individuals, representing multiple generations, multiple family groups. Some are working on stone tools by the light of the fire. Some are working hides, stretching and treating them for use as coverings or containers. Some are simply resting, their bodies warmed by proximity to the fire. As darkness deepens, as the night grows late, the activity slows. The fire is banked, allowed to burn down to coals that will smoulder through the night and be rekindled in the morning. People settle into sleep, perhaps in clusters for warmth, perhaps wrapping themselves in those hides that have been treated and prepared. Their sleep is different from the sleep of other animals. It is not the light sleep of prey animals, alert to danger, ready to flee. It is a deeper sleep, more consolidated, yet still capable of being broken by alarm or danger. In the darkness, with the warmth of the fire and the presence of others, sleep comes more easily than it would in the open, on the ground, exposed to the night. And as the night deepens, as sleep claims these people one by one, their brains continue their work. In their dreams, experiences of the day are being consolidated. Memories are being formed. Skills are being practiced and refined in the space of sleep. The neural connections that were forged during the day's activities are being strengthened. The body is resting, healing, preparing itself for the next day's activities. The compression of human sleep, that efficiency of sleep that we discussed earlier, is allowing a more intense restoration of the body and mind in a shorter period of time. By the time the fire is rekindled in the morning, the people of this shelter have been thoroughly rested, ready to face another day. The control of fire, then, was not merely a practical achievement, not just a way to cook food or warm the body or defend against predators. It was also a transformation of sleep, a transformation of the night itself, a transformation of the rhythm of human existence. It was the beginning of the conquest of darkness, the beginning of the human ability to extend activity beyond the reach of daylight, the beginning of the long process that would eventually lead to electric lights and 24-hour activity cycles, and all the complications and benefits of modern human life. But in those ancient caves, the fire was simple, direct, essential. It was warmth and light and safety all in one. Now, as we follow Homo erectus on their great dispersal out of Africa, we must understand that they were not leaving Africa because they were forced to, or because Africa was no longer suitable for habitation. Rather, they were spreading because they could, because their biology and their culture had reached a point where range expansion became possible. The world was calling to them, in a sense, and they were equipped to answer that call. But the path out of Africa was not open at all times. The geography of the world during the Pleistocene was not static. The climate was changing constantly, driven by vast astronomical cycles known as Milankovitch cycles. These cycles, named after Serbian scientist Milutin Milankovic who first proposed them, result from slight variations in the Earth's orbit around the Sun and variations in the tilt of the Earth's axis. These are not small variations. They are significant changes that affect the amount of solar radiation reaching different parts of the planet, particularly at different latitudes. The orbital variations occur on several different timescales. The Earth's orbit around the Sun is not perfectly circular. It varies between more circular and more elliptical over a period of about 100,000 years. When the orbit is more elliptical, the difference between the closest approach to the Sun, perihelion, and the farthest distance from the Sun, aphelion, is greater, and this affects the distribution of solar radiation. At the same time, the tilt of the Earth's axis relative to the orbital plane varies between about 22.1 and 24.5 degrees over a period of about 41,000 years. This tilt is responsible for the seasons. When your hemisphere is tilted toward the Sun, you experience summer, and when it is tilted away, you experience winter. A greater tilt means more extreme seasonal variation. Additionally, the Earth's axis itself is precessing. It is slowly rotating like a spinning top, completing one full rotation every 26,000 years. This means that the direction in which the axis points gradually changes. The North Star, Polaris, is the current direction of the North Pole, but thousands of years ago the axis pointed in a different direction. These three cycles combine and interact with each other in complex ways. Sometimes they reinforce each other, leading to more dramatic climate shifts. Sometimes they partially cancel each other out, leading to smaller variations. But the net result is that the climate of the Earth is constantly changing on timescales of tens of thousands of years, over timescales of 20,000 to 40,000 years, which is to say, over timescales that are significant in terms of evolutionary and human historical time, but which are trivially small in terms of geological time. The climate could shift dramatically. Ice ages would come and go. The great ice sheets that cover the poles would expand, covering more of the continents and then retreat. The sea level would rise and fall by hundreds of meters, exposing land bridges that are now underwater and submerging coastal areas that are now dry land. Desert regions would become lush grasslands filled with water sources and abundant vegetation, and grasslands would turn back to desert as the climate shifted. This constant variation provided the canvas upon which human evolution would paint its grand story. One of the most important of these climate cycles involves the Sahara Desert, that vast expanse that today covers much of northern Africa, nearly 9 million square kilometers of sand, rock and dunes. The Sahara is one of the largest deserts in the world, comparable in size to the continental United States. To cross it on foot is a feat of extraordinary endurance and difficulty. The temperatures soar above 50 degrees Celsius in summer. Water sources are few and far between. The landscape appears almost lunar in its barrenness. Many people assume that the Sahara has always been desert, a permanent barrier to human movement, separating sub-Saharan Africa from the Mediterranean world. But this is not the case. The assumption reveals an error in our thinking. We tend to imagine the world as static, unchanging, but geological and climate history reveals a world in constant transformation. During certain periods of geological time, the Sahara was green. Driven by Milankovitch cycles, the climate would shift toward a configuration that brought more moisture to northern Africa. The monsoon rains that today fall primarily in the Sahel region, just south of the Sahara, would shift northward, reaching further into what is now desert. The Sahara would transform almost unimaginably. Grasslands would appear, vast savannas of green grass stretching from horizon to horizon. Trees would take root, acacias and date palms and other drought-tolerant species. Lakes and rivers would flow where now there is only sand and rock. Vegetation would support wildlife, herbivores and carnivores, insects and birds. The desert would bloom. These periods are called the Sahara pump phases because they acted like a pump in a mechanical sense, drawing populations northward when conditions became favourable and then pushing them back southward when the climate shifted back to aridity. During the green phases, human populations would expand northward. Following the animals and the water sources, they would discover new territories, new hunting grounds, new areas suitable for human habitation. But then, gradually, the climate would shift back. The monsoons would retreat southward, the rains would stop, the grass would wither, the trees would die, the lakes would dry up. The populations would face a choice: attempt to remain in the increasingly arid territory and risk starvation, or withdraw back to the south, to regions where water and vegetation were still abundant. One of the greenest periods in the Sahara's recent geological history occurred around 2.1 million years ago, right at the time when Homo erectus was beginning to emerge and expand out of its original range in East Africa. The timing may or may not be a coincidence. The evidence is not entirely clear about whether Homo erectus specifically dispersed during this green phase, or whether they dispersed more gradually over multiple climate cycles. But what is clear is that when the Sahara was green, it provided a corridor, a pathway for human movement from the African continent northward toward the Mediterranean, toward Europe, toward Eurasia. The animals that humans hunted, buffalo, elephants, horses, would also have been drawn northward by the availability of vegetation and water. The humans, following these animals, would have naturally expanded their range. The Green Sahara became a migration highway, a route through which populations could flow northward to colonize new territories. This cycle of climate change, of the opening and closing of migration corridors, would repeat over and over again during the nearly 2 million years of Homo erectus existence. We can identify at least 20 major green phases in the Sahara during this time period. Multiple times the Sahara would green, and populations would expand northward. Multiple times the Sahara would desiccate, and populations would be pushed back southward or isolated in refugial areas. Some populations might have remained in northern refugia, in places where permanent water sources and vegetation persisted even during dry phases. Others would have been forced to retreat. The result was a complex pattern of dispersal and contraction, expansion and retreat, that would shape the distribution of Homo erectus across Africa and eventually across the Old World. This cycle of climate change, of the opening and closing of migration corridors, would repeat over and over again during the nearly 2 million years of Homo erectus existence. Multiple times the Sahara would green and populations would expand northward. Multiple times the Sahara would desiccate, and populations would be pushed back or isolated in refugial areas. The result was a complex pattern of dispersal and contraction, expansion and retreat that would shape the distribution of Homo erectus across Africa and eventually across the Old World. So let us imagine Homo erectus, a group of them, perhaps 20 or 25 individuals strong, moving northward through the Green Sahara. It is 1.8 or 1.7 million years ago during one of the favourable climate periods. The landscape around them is grassy, with scattered trees providing shade and food, seeds, fruits, leaves. The trees are primarily acacias, with their characteristic flat-topped crowns and thorny branches. Beneath these trees, the grass grows in response to the moisture brought by the northward shifted monsoons. Water is available from seasonal rivers and from lakes that dot the landscape. Some of these lakes might be quite large, with abundant fish and aquatic plants. They are following herds of large animals, possibly including the ancestors of modern buffalo, possibly including early forms of elephant, possibly including horses and other grazers. These animals are also drawn northward by the availability of fresh grass and water. The hunting is good, food is abundant, the climate is favourable, the conditions are ideal for human expansion and population growth. The journey northward is a gradual transition. It takes many generations, many hundreds of years. We should not imagine this as a deliberate migration with a specific destination in mind. Rather, it is a slow expansion, with groups moving a few kilometres each generation, following the animals, discovering new water sources, establishing themselves in new territories. Over the course of perhaps 500 or 1,000 years, the population reaches the Levant region. The journey has taken them gradually out of the purely tropical climate of sub-Saharan Africa and into more temperate zones. The vegetation begins to change, trees become more frequent, the grass changes in character, the animals change as well. The large buffalo and elephants give way to smaller herbivores, to animals better adapted to Mediterranean climates. As they continue northward, they eventually reach the Levant, the region that includes modern-day Israel, Palestine, Syria, Lebanon and Jordan. This region sits at a crucial geographic crossroads, where Africa meets Asia, where the African continent extends northeastward to meet the Eurasian continental mass. The Mediterranean Sea is to the west, the Arabian Desert to the east. The Levant is a narrow corridor, a bridge between continents. This region, during the Pleistocene, was more forested than it is today, with woodlands dominated by oak, olive and pistachio trees. The landscape is hilly and variable, with rivers and streams providing abundant water. The climate was Mediterranean, warm and dry in summer, cool and wet in winter, more extreme in seasonal variation than the tropical African climate they had left behind. The landscape is more temperate, the vegetation more diverse, the animals different from those of Africa, and yet it is not unrecognizable. These are still animals that Homo erectus has some experience hunting. The climate is challenging but not impossible to adapt to. The opportunities are present for a human population to establish itself. At a site called Ubaydiyah, located just 3 kilometers south of the Sea of Galilee, archaeologists have found extensive evidence of Homo erectus occupation. The site dates to around 1.5 million years ago, placing it firmly within the time of Homo erectus dispersal into the Levant. The archaeological context suggests a woodland environment, with oak, olive, and pistachio trees creating a forest landscape interrupted by clearings and grasslands. The fauna recovered from the site includes hippopotamuses and rhinoceroses, along with more temperate animals like wild boar. Stone tools, including hand axes, are found in association with animal remains, suggesting hunting and butchering. What is remarkable about Ubaydiyah is that it represents one of the earliest Acheulean sites outside of Africa. The hand axes found there are sophisticated and symmetrical, showing the same hallmarks of craftsmanship that we see in East African sites. This tells us that the technology was not left behind when Homo erectus moved north. Rather, the technology moved with them, and they continued to refine and develop it in their new location. The humans who made these tools were not less capable than their African counterparts. They were the same species, using the same technology, adapted to slightly different environments. Continuing eastward and northward from the Levant, Homo erectus groups would have encountered the Caucasus Mountains, the great mountain range that divides Europe from Asia. Archaeological evidence suggests that Homo erectus crossed this barrier and reached the Caucasus region. At a place called Dmanisi in the country of Georgia, scientists have made some of the most remarkable discoveries in paleoanthropology. At Dmanisi, archaeologists led by David Lord Kipanidze have excavated 5 skulls dating between 1.85 and 1.77 million years ago, making them roughly contemporary with the earliest dispersal events we are discussing. These 5 skulls tell an extraordinary story. They show significant variation, more variation than we might expect within a single species. One skull, catalogued as D3444, has been nicknamed the Toothless Old Man, because the individual lost all of their teeth long before death. The jaw shows evidence of remodelling and adaptation to life without teeth. This is a remarkable discovery because it suggests something important about Homo erectus society. An individual without teeth would have had tremendous difficulty feeding themselves on the typical diet of the time. Without teeth, they could not process tough plant material effectively, and they would have had difficulty tearing meat. Yet this individual survived. They survived long enough after losing their teeth for significant bone remodelling to occur. The only explanation is that other members of the group were actively providing food to this individual, helping them to eat, caring for them despite their disability. Another skull from Dmanisi, catalogued as D4500 and sometimes called Skull 5, presents a different puzzle. This individual had a brain volume of only 546 cubic centimetres, smaller than the average Homo erectus brain, in fact smaller than some later Homo habilis individuals. Yet the rest of the skull shows clear characteristics of Homo erectus, including the particular shape and structure of the jaw and the overall morphology. How could an individual with such a small brain, with less neural capacity than ancestors who came before, be classified as Homo erectus? A recent study published in PLOS One in January 2026 proposed an extraordinary answer. Looking at the anatomy of all 5 Dmanisi skulls, researchers noticed that while some features clearly aligned with Homo erectus, other features seemed to align with earlier forms, possibly even with the Australopiths that had preceded Homo erectus in Africa. The researchers proposed that the Dmanisi population might not have been a single, homogeneous species, but rather a mixture of different groups, perhaps including multiple species that had dispersed out of Africa together in the same time period. This raises a revolutionary possibility, that the dispersal of Homo erectus out of Africa was not the sole dispersal event in human evolutionary history, but rather that multiple human species may have left Africa together in the same migration event, creating a more complex pattern of human dispersal than we had previously imagined. This proposition, while still debated, is fascinating and somewhat humbling. It suggests that our understanding of human evolution is more incomplete than we have acknowledged, that there is more going on in the fossil record than a simple linear progression from earlier to later forms. The world was more complex, more diverse, more interesting than a simple narrative can convey. There were multiple experiments being conducted simultaneously, multiple versions of humanity existing at the same time, exploring different solutions to the problem of surviving in a changing world. The toothless old man of Dmanisi, with his surviving members supporting him after tooth loss, is a powerful image. It tells us that Homo erectus had developed a level of social complexity and compassion that we might not always associate with our ancient ancestors. They were not brutish killers, not simple survival machines. They were individuals capable of recognizing distress in others, capable of providing care, capable of ensuring that a disabled member of the group could continue to eat and survive. This is not instinct alone. Many animals care for their young, but rather a deliberate social practice, a collective decision that this individual's life was worth supporting, worth extending even in the face of physical disability. Let your imagination dwell now on this scene. A group of Homo erectus at Dmanisi, perhaps 1.8 million years ago. The toothless old man is sitting within the group, perhaps near a fire or near a gathering place, positioned where he can see the river and watch the other members of the group moving about their daily tasks. His name is lost to history, as are the names of all his companions. We know him only by his catalogue number, D3444, and by the nickname that paleontologists have given him, the Toothless Old Man. But he was a real individual, a real person, with a personality and a history and a role within his group. The story that his skull tells is one of profound suffering and resilience. All of his teeth were lost before his death, not gradually, in the way that modern humans might lose teeth in old age. Rather, all at once, or over a relatively short period. This might have been due to gum disease, to infection, to trauma, to some other cause. Whatever the cause, the loss of all teeth was a catastrophic event. Without teeth, this individual could not process hard plant material. He could not tear meat with his teeth. He could not eat anything that required mastication. He would have starved, unless his group intervened. And they did intervene. His companions brought him meat from the day's hunt, meat that has been carefully prepared, broken into pieces that do not require chewing, softened in the heat of the fire. Perhaps they pre-chewed the meat for him, the way modern humans sometimes do for infants or elderly individuals. Perhaps they reduced the meat to a paste by cooking it for extended periods. Perhaps they extracted bone marrow and fed him that, along with soft plant foods. However they did it, they kept him alive. They ensured that he had food. They cared for him despite his disability. They did not see him as a burden to be abandoned, but as a member of the group, as someone whose continued existence matters. How long did he survive after losing his teeth? The evidence suggests that it was for a considerable period. The jaw shows evidence of remodeling, of changes to the bone structure that would take months or years to develop. The teeth are completely gone, not just loose or decayed. The bone of the jaw has actually reshaped itself to accommodate the absence of teeth. This is a process that takes time. It suggests that the individual lived for months, if not years, after losing his teeth. All of this time, he was dependent on the care of others. All of this time, the group was allocating resources to keeping him alive. This is what it means to be human, in at least one important sense. It is the capacity to care beyond the boundaries of immediate kin, the capacity to extend effort and resources to individuals who cannot care for themselves. It is the ability to recognize that another individual's suffering matters, that their life has value, that the community is stronger and better for the decision to care for them. This capacity may have begun to emerge in Homo erectus. It was definitely present by the time of the Neanderthals, who show clear evidence of caring for disabled and injured individuals. And it is certainly present in modern humans, where we have elaborate social systems devoted to caring for the young, the old, the sick, and the disabled. But perhaps it began here, 1,000,000 years ago, in a group of early humans at Dmanisi, who made the decision to keep alive an old man who had lost his teeth and who could not feed himself. They sit with him, they are present with him, they ensure that he has food. Perhaps in the evening, as the fire is burning, someone sits beside him and tells him stories that he cannot understand if language has not yet developed, but that he can appreciate for their tone and emotional content. Perhaps someone touches his shoulder gently, offering comfort. Perhaps someone shows him something beautiful, a well-made hand axe, a colourful stone, the sight of stars in the night sky. We cannot know these details. We can only infer from the bones that he was cared for, that he was valued, that his life mattered to his group. From Dmanisi, the dispersal continued. Homo erectus populations moved further east and north, eventually reaching China. At a site called Yongxian in China, skulls have been recovered that show clear Homo erectus features. For many years, these skulls were thought to date to around 1.1 million years ago, placing them well after the Dmanisi dispersal. But a groundbreaking study published in February 2026 in Science Advances used a new dating technique, a method involving aluminum-26 and beryllium-10 isotopes, to re-evaluate the age of the Yongxian skulls. The results were astonishing. The skulls were not 1.1 million years old, they were approximately 1.77 million years old, nearly as old as the Dmanisi skulls. This means that the dispersal of Homo erectus across Asia happened incredibly rapidly, faster than anyone had previously imagined. Groups that had left Africa perhaps shortly after Homo erectus emerged as a distinct species had already reached China within only 100,000 years or so. This incredible pace of expansion suggests that the dispersal was not a slow, cautious movement, but a rapid, almost explosive radiation out of Africa and across the Eurasian continent. Imagine this rapid expansion. Imagine Homo erectus populations year after year, generation after generation, moving further from the homeland, exploring new territories, encountering new animals, adapting to new climates. Some groups moved northward, following the animals and the climate corridors into the temperate zones. Some groups moved eastward, eventually reaching the great river systems of Asia, the Yellow River, the Yangtze, the Ganges. Some groups, perhaps split from the main population, turned southward, moving into Southeast Asia, into the regions that are today Thailand, Malaysia, Sumatra. The movement into Southeast Asia represents a particularly dramatic moment in human history. For the first time, human populations were moving into regions that required crossing water. During the Ice Ages, when sea levels were lower, the continental shelves were exposed and there were land bridges connecting islands and peninsulas that are now separated by water. The Sundanese Shelf, called Sunderland, connected Java, Sumatra and Borneo to the Asian mainland during glacial periods when sea levels dropped by 120 metres or more. Homo erectus could have walked to Java when the sea level was low, but there was a barrier even in the most favourable conditions. East of Java and Bali lay deeper ocean, the Wallace Line, a geographic boundary first identified by the naturalist Alfred Russel Wallace, which separates Asian fauna from Australian fauna. This line represents the easternmost extent of large placental mammals in the fossil record. Crossing this line required crossing open water. There was no land bridge, no matter how low the sea level dropped, and yet there is evidence that Homo erectus did cross this barrier. In 2025, researchers reported the discovery of stone tools on the island of Sulawesi, tools that dated to approximately 1.04 million years ago. These tools were not simple and crude. They showed sophistication and purpose. The island of Sulawesi is located east of the Wallace Line in deeper ocean, where ocean currents are strong and the water is relatively deep. The Wallace Line separates the fauna of Asia from the fauna of Australia and the Pacific Islands. Animals and plants do not easily cross this boundary. There is no land bridge that would have connected them even during the Ice Ages when sea levels were significantly lower. The implications of finding human tools on Sulawesi are staggering. Homo erectus at some point crossed at least 50 kilometres of open water to reach Sulawesi. They did not have boats, at least not boats in the modern sense, with carefully constructed hulls and navigation tools, sails and rudders. There is no evidence of such boat-building technology at this time period. The most likely explanation is that they were carried across on floating vegetation, mats of vegetation, dead tree trunks, or pieces of forest that broke off and floated into the ocean during storms or floods. Such floating vegetation mats can carry surprising amounts of material. They can support the weight of animals. Ocean currents are powerful, and they could carry a vegetation mat across the Wallace Line to land on the shores of Sulawesi. Perhaps a group of Homo erectus was caught by a severe storm while living on coastal areas or low-lying floodplains. The floodwaters rose, perhaps due to unusual tidal surges or seasonal flooding. A floating mat of vegetation became detached from the shore and was pulled out to sea. The group clinging to this mat found themselves swept away from land, moving farther and farther from the familiar shore. Hours passed, then days. The mat drifted in the ocean currents, moving with the flow of the water. The crossing would have been harrowing. There would have been no fresh water, no food, no shelter from the sun and the waves. Some members of the group may have been lost to the sea, others would have clung to the mat trying to survive the ordeal. And somehow, through luck and circumstance, the mat was carried across the Wallace Line, across 50 kilometres or more of open water, and washed ashore on the island of Sulawesi. The survivors found themselves on a new island, a place they had never seen before, inhabited by animals they did not know, with plants they did not recognise. The initial situation would have been dire, cast away on an unknown island, separated from their homeland, uncertain whether they could survive in this new place. And yet, what is remarkable is that these accidental castaways survived. They established populations, they adapted to the island environment. They continued to make tools and to hunt and to reproduce. They passed their knowledge and skills onto their descendants. The tools they made on Sulawesi show continuity with mainland traditions. The same basic techniques, the same approaches to stone knapping, but also local adaptation, showing that populations had time to develop and diverge before losing contact with the mainland. The accidental colonists had become successful colonizers, had established themselves so firmly that their descendants continued to inhabit the island for hundreds of thousands of years, until eventually being replaced by other populations as human evolution continued its complex dance across the Indonesian archipelago. The colonization of Sulawesi was just the beginning. Over the following million years, Homo erectus populations spread throughout Southeast Asia and the Indonesian archipelago. At a site called Liang Bua, on the island of Flores, is a cave system that would eventually yield the remains of Homo floresiensis, the remarkable hobbit species that we will discuss shortly. But the earlier layers of this cave, dating to more than 100,000 years ago, contained stone tools and evidence of human occupation. These tools are attributed to Homo erectus, or possibly to transitional forms between Erectus and Floresiensis. Homo floresiensis is one of the most fascinating discoveries in paleoanthropology. First described in 2003, Homo floresiensis was initially shocking to many researchers. These individuals were small, approximately 1.1 meters, or about 3 feet 7 inches tall. The brain was proportionally small as well, approximately 380 to 430 cubic centimeters, smaller even than the smallest-brained Homo erectus individuals. Yet there was no question that they were human, that they were tool makers, that they were hunters. Floresiensis is interpreted as a descendant of Homo erectus that evolved smaller body size in response to the island environment of Flores. This process is called island dwarfism, and it occurs when populations of large animals become established on islands with limited food resources. The selective pressure favours smaller individuals who require less food to survive and reproduce, and over generations the average body size of the population decreases. Something similar happened in elephants on islands in the Mediterranean, resulting in tiny elephant species no larger than sheep. The same process, applied to Homo erectus on the island of Flores, resulted in Floresiensis. But Floresiensis was not helpless or limited. They hunted pygmy elephants called stegodon, animals that weighed several hundred kilograms and were far larger than the Floresiensis hunters. A stegodon could weigh 5 or 6 times as much as an adult Floresiensis individual. Yet these small humans managed to hunt and kill these massive animals repeatedly. To successfully hunt such a large animal, the Floresiensis hunters would have needed to work in groups, probably with at least 10 to 15 individuals participating in each hunt. They would have needed to use sophisticated hunting techniques, perhaps driving the animal into a trap or ravine, perhaps using fire to confuse or injure it, perhaps attacking it simultaneously from multiple directions. They would have needed to plan their hunts carefully, to understand the behaviour of the stegodon, to know where the animals watered and grazed. They would have needed to coordinate their activities across multiple individuals, communicating in some fashion, agreeing on a plan, executing that plan in a coordinated manner. All of this required intelligence, planning, social complexity. They used fire, as evidenced by burned bone and ash deposits in the cave system of Liangbua, where many of their remains have been found. They made elaborate tools, including shaped spearheads and bone implements. They created stone blades and pointed implements suitable for hunting. They were fully human in their behaviour, even if their bodies were dramatically smaller than those of their ancestors. Their brain size was small, their stature diminutive, yet their intelligence and capability were not thereby diminished. They were a fully functional human society, living successfully on their island for hundreds of thousands of years, representing a remarkable experiment in island adaptation and human resilience. Recent research has cast new light on the extinction of Floresiensis. In 2025, a detailed study combining radiometric dating with analysis of stalagmite records and tooth isotopes revealed that Floresiensis disappeared around 61,000 to 55,000 years ago, a period that coincides with a severe drought on Flores. The researchers studied stalactites and stalagmites from caves on Flores, measuring the isotopic ratios of oxygen and carbon to determine the precipitation patterns of the past. They also analysed tooth enamel from stegodon and other animals, using isotope ratios to determine their diet and the amount of vegetation available. The combined evidence told a clear story. Rainfall fell to approximately half of modern levels. The climate shifted dramatically toward aridity. The vegetation that sustained the stegodon herds and provided plant foods for the Floresiensis population would have been severely reduced. Forests became more open, grasslands became drier. The lakes and water sources that had been reliable dried up. With less food available, the populations began to contract. The stegodon herds became smaller. The Floresiensis population declined. Eventually, they disappeared entirely. This is a poignant ending to the Floresiensis story. They had survived on their island for nearly 1 million years, longer than modern humans have existed as a distinct species. They had adapted to an entirely new way of living, had developed technologies and social structures suited to their environment. They had learned to hunt large prey that were much bigger than themselves. They had learned to use fire to make tools, to live as a complex social group. They had thrived. But then the climate shifted, and they could not adapt quickly enough. The change was too rapid, too severe. They became extinct, leaving only their bones and their tools as testament to their existence. What is remarkable is that this extinction story is probably not unique to Floresiensis. Similar extinctions were probably happening throughout the world as climate shifted and changed. Species that had been successful in one climate regime found themselves unable to survive in the new regime. Island populations in particular were vulnerable. An island represents a closed ecosystem. When the climate on an island changes, there is no place to flee, no way to escape to more favourable conditions. The population either adapts or goes extinct. Floresiensis could not adapt quickly enough. So also with Homo erectus. Though their extinction took place more slowly, over a longer period of time, it was fundamentally related to the same vulnerability. The inability to thrive in a radically changing world, the replacement by species that were better adapted to the new conditions. In this, they are like countless other species that have gone extinct throughout Earth's history. We know from the fossil record that extinction is the fate of nearly all species. Extinction is not a failure, not a tragedy in some moral sense. It is simply the natural endpoint for species that no longer fit the environmental conditions in which they find themselves. But for the individuals of that species, extinction is indeed a tragedy. It is the end of their world, the end of their traditions, the end of their knowledge and skills and capabilities. The last Homo erectus individual who ever lived was unaware that they were the last. They lived their life, faced their daily challenges, interacted with their group, and then died. And with their death, a species that had existed for nearly 2 million years came to an end. Floresiensis and Homo erectus are also like our own human ancestors in their vulnerability to environmental change, in their dependence on stable conditions, in the fragility of human existence in the face of planetary climate shifts. Modern humans like to imagine ourselves as masters of our environment, as beings whose technology insulates us from the challenges of climate and geography. And to a certain extent, that is true. But the deeper truth is that we are still products of evolution, still adapted to particular environmental conditions, still vulnerable to rapid change. The climate crisis facing our planet today is a reminder of this fundamental vulnerability. Our species is incredibly adaptable and innovative, but we are not infinitely so. We too face the possibility of conflict with our environment, of inability to adapt quickly enough to catastrophic change. The extinction of Floresiensis and the eventual replacement of Homo erectus by other species serves as a humbling reminder of our own possible fate. As we trace the persistence of Homo erectus across these vast distances and time spans, we must not forget their ultimate fate. For nearly 2 million years, this species persisted. For nearly 2 million years, Homo erectus adapted, migrated, innovated, and survived. They created tools of increasing sophistication. They mastered fire. They developed hunting techniques that allowed them to harvest large animals. They established themselves on multiple continents. They evolved into multiple forms adapted to local environments, creating diversity within the species. And then, gradually, they began to decline. The last known populations of Homo erectus persisted in Southeast Asia. At a site called Ngandong on the Solo River in Java, 12 skullcaps were discovered between 1931 and 1933. These are the most complete remains of the latest Homo erectus, the populations that survived the longest, that held out the longest against the tide of evolutionary change that was sweeping through the human lineage. The Solo River is a major river in Java, flowing through lush tropical forest. The site of Ngandong is located in one of these terraces created as the river cut deeper into the landscape over countless millennia. The skull caps themselves are remarkable. They are relatively thick, robust, clearly showing the characteristics of Homo erectus, but also showing the highest level of brain size achieved by the species. For many years, the age of these Ngandong skulls was uncertain. This is a common problem in paleoanthropology. Dating ancient specimens is not straightforward. Different dating techniques gave different results, ranging from as recent as 50,000 years ago to as ancient as 200,000 years ago. When you have such a wide range of possible dates, it makes it difficult to understand exactly when these individuals lived and how they fit into the broader pattern of human evolution. The uncertainty created a kind of mystery surrounding the Ngandong specimens. Were they from the Middle Pleistocene or the Late Pleistocene? Were they contemporary with other Homo erectus populations, or were they much later? The answer was crucial for understanding the timeline of human evolution. But in 2019, a comprehensive study attempted to resolve this uncertainty. The researchers, working with the specimens and the deposits, recognized that the traditional dating methods had significant limitations. Some techniques gave dates that were clearly outliers, far outside the range of other dates. The researchers needed a new approach. They collected 52 separate radiometric dates from various parts of the Ngandong deposits, using multiple dating techniques and samples. Radiometric dating works by measuring the decay of radioactive isotopes trapped in rocks or other materials. Different isotope systems decay at different rates and can be used to date materials of different ages. By using multiple different dating systems and multiple samples, the researchers could compare the results and identify which dates were most reliable. When all of these dates were analysed together and the outliers were considered, a pattern emerged. The Ngandong skull caps dated to approximately 117,000 to 108,000 years ago. This is a remarkably late date for Homo erectus. This means that Homo erectus persisted on the island of Java, in this location, until very late in the Pleistocene, very near the end of an entire era of the Earth's history. The latest Homo erectus were walking the Earth when our own species, Homo sapiens, was only beginning to evolve and spread out of Africa. The two species were coexisting, albeit in different locations, for at least some period of time. These final Homo erectus of Java were, in many ways, the most advanced representatives of their species. The skulls show a level of brain complexity and size approaching, or perhaps equal to the maximum achieved by the species. Their tools were sophisticated. There is evidence that they used fire. Everything suggests that they were fully capable of surviving and thriving. Yet they eventually vanished, replaced by other human species, or simply fading away as populations contracted and finally ceased to reproduce. The story of the Ngandong skulls is made all the more poignant by the history of one particular population of Homo erectus remains, Peking man. Acheulean, a cave complex near Beijing, was the site of one of the most important paleoanthropological discoveries in history. Beginning in the early 20th century, researchers excavated at Acheulean and recovered the remains of approximately 40 individual Homo erectus, represented by about 200 bones, spanning hundreds of thousands of years. These were among the most important specimens of Homo erectus ever recovered, providing invaluable information about the anatomy, the behaviour, the pathology, and the distribution of the species. But tragedy befell these specimens. As World War II raged in the Pacific and as Japan invaded China, Acheulean was seized by Japanese troops. American military officials decided that the specimens should be evacuated, removed from China to safety. In December 1941, an American military convoy began to transport the remains of Peking man toward the coast, where they would be placed aboard a ship and transported to the United States. But that ship was seized during the Japanese attack on Pearl Harbor, and the remains of Peking man were lost. The bones of Homo erectus, preserved for nearly 1 million years, were lost in the chaos of human warfare and have never been recovered. There is a poignant irony here. An American Marine named Richard Bowen participated in the evacuation attempt. In 1947, after the war had ended, Bowen reported that he had discovered some bones in a foxhole at Qinhuangdao, a port city east of Beijing. He believed these might be bones of Peking man that had been lost during the evacuation. The bones were not authenticated at the time, and Bowen eventually returned to the United States. He did not have direct proof of what he had found. Over the decades, his story became increasingly forgotten, overshadowed by more recent discoveries and new research. In 2006, a committee was established to search for the lost remains of Peking man. Archaeologists and paleontologists travelled to potential locations, searching for any remaining specimens. They searched the Qinhuangdao area, where Bowen claimed to have found bones. The Acheulean site was carefully excavated, in case any specimens had been missed or hidden. But no bones of Peking man were recovered. The mystery remained unsolved. It is a melancholy reminder of how much human history we have lost, how much knowledge and understanding has been erased by accident, by war, by the vagaries of human chance. What we do know is that late Homo erectus in China was sophisticated and successful. Multiple sites across China have yielded evidence of Homo erectus occupation spanning hundreds of thousands of years. At one site in China, teeth have been recovered that date to approximately 300,000 years ago, very late in the Homo erectus timeline. These teeth are interesting because they show characteristics suggesting possible interbreeding between late Homo erectus and early Homo sapiens. If this interpretation is correct, it means that these two species, these two distinct forms of humanity, were not completely isolated from each other, but were in contact, were perhaps even capable of producing offspring together. This raises deep questions about the nature of species boundaries, about how we define human, about the fluidity and interconnection of human populations across the globe. The coexistence of Homo erectus and Homo sapiens, at least in some regions during the late Pleistocene, suggests a more complex picture than we might have previously imagined. These two species did not simply replace each other in a single dramatic moment. Rather, there was a period of overlap, a period when both species existed on the same continents, in some cases perhaps even in the same regions. During this period, genetic exchange might have occurred. Populations might have sometimes competed for the same resources, and sometimes avoided each other. The transition from one form of humanity to another was not a sharp boundary, but a gradual blurring and shifting of boundaries. But gradually the reign of Homo erectus came to an end. By 100,000 years ago, or perhaps a bit earlier, Homo erectus was gone. They had left no direct descendants, no population that continued their lineage into the modern world. They had been replaced by other human species, by Homo neanderthalensis in Europe and Western Asia, by Homo sapiens, our own species, spreading out of Africa. The span of nearly 2 million years during which Homo erectus had dominated the human world had come to an end. What did Homo erectus leave behind? What is their legacy to us, their distant evolutionary descendants? They left a world that was more thoroughly human than it had been before. The continents were now populated by humans. The technology of fire was in place, passed on to successor species who would continue to refine it and use it. The foundation of tool-making, of purposeful creation of objects to suit particular needs, was firmly established. The capacity for abstract thinking, perhaps, was beginning to emerge, as evidenced by the symmetrical hand axes and the care given to disabled individuals like the toothless old man of Dmanisi. Homo erectus showed that humans could adapt to virtually any environment on Earth. They survived in the heat of Africa and in the temperate zones of Eurasia. They adapted to the tropical rainforests of Southeast Asia and to the savanna grasslands of Africa. They demonstrated that human beings, with our upright posture, our increasingly large brains, our capacity for tool-making, our social structures, could expand across the globe and establish themselves in diverse environments. This capability, this adaptability, this drive to explore and expand has persisted in their descendants. It is part of the human inheritance. We might also say that Homo erectus left behind a kind of template for human existence. They established patterns that have continued throughout human history. They hunted large animals, they gathered plant foods, they used fire, they made tools, they lived in social groups, they cared for their disabled and their young. All of these patterns, established over nearly 2 million years by Homo erectus, have continued in their descendants. We still hunt animals, though now through farms and processing plants, rather than through persistence hunting. We still gather plant foods, though now from gardens and stores. We still use fire, though now in stoves and power plants rather than in hearths and caves. We still make tools, infinitely more sophisticated tools, but tools nonetheless. We still live in social groups. We still care for the disabled and the young. We are still, in many ways, Homo erectus, merely with larger brains and more sophisticated technologies. And perhaps this is the deepest legacy of Homo erectus. They show us what humans are at a fundamental level, not the Consider their capacity for care, exemplified by the toothless old man who was fed and cherished despite his disability. Consider their courage, demonstrated in crossing the Wallace Line, reaching islands where no humans had ever reached before. Consider their perseverance, surviving for nearly 2 million years, adapting to continents and climates, maintaining cultures across thousands of generations. They are gone now, utterly gone. Not a single Homo erectus walks the earth. Yet they left their mark. They left their bones carefully excavated and studied, telling us their story. They left their tools, their hand axes and their scrapers and their evidence of fire. They left the blueprint of human possibility, the template of human nature that we continue to embody in our own existence. And perhaps, in some mysterious way that we do not fully understand, they left something in our own genes, in the DNA that we carry in our cells, in the basic structure of our bodies and our minds. That inheritance is real and tangible. Let us take a moment now to contemplate what it means to be Homo erectus, to inhabit that particular evolutionary moment, to live as that particular form of human being. Imagine yourself transformed, your legs longer, your brain larger than your ancestors but smaller than your successors, your skin dark brown, your body lean and muscular. Imagine yourself living in a world without writing, without agriculture, without cities or civilizations, but also a world where you have fire, where you make sophisticated tools, where you live in complex social groups, where you care for your disabled and your young. What would drive you forward? What would motivate you to leave the homeland, to cross vast distances, to establish yourself in new and unknown lands? It would not be some great conscious plan, some grand strategic vision to conquer the world. Rather, it would be the accumulation of small decisions and circumstances. A good year leads to population growth and the population becomes denser. Competition for resources increases. A young group, perhaps headed by an ambitious leader, or perhaps simply by chance, moves away from the main population. They follow herds of animals. They discover new water sources. They find themselves in a new territory. They adapt. They thrive. Over generations, the group expands. More groups bud off and move further. The process repeats, over and over again, until populations have spread across continents. This process is not unique to Homo erectus. Modern humans did something very similar, spreading from Africa to every continent on Earth, establishing themselves in every possible habitat from tropical rainforest to frozen tundra, to high mountain peaks to desert islands. But Homo erectus was doing this first, was pioneering the pathways that their successors would later follow. They were learning how to migrate, how to adapt, how to conquer new territories. This capacity, this willingness to explore and expand, this drive to move beyond the horizon has become one of the defining characteristics of humanity. It is written in our genes, inherited from our ancestors, refined and perfected by millions of years of evolution. The technological development of Homo erectus was not a random process. It was driven by practical needs and challenges. When they encountered new environments, they needed new tools to deal with those environments. When they encountered new prey animals, they needed new hunting techniques. The hand axe, while it may have had symbolic or status functions, was primarily a tool for butchering large animals, for processing carcasses, for extracting meat and bone marrow. As Homo erectus spread across the world, they encountered different animals, different plants, different seasonal patterns. The tools and techniques evolved to match these new realities. Think about the cognitive capabilities that this required. To manufacture an Acheulean hand axe, the maker needed to envision the final form, to understand how stone fractures and flakes, to plan a sequence of strikes that would gradually transform the raw nodule into the desired shape. This requires abstract thinking, planning, mental visualization. The individual had to be able to imagine a form that did not yet exist in the stone, and then execute a plan to bring that form into being. This is not simple instinctive behavior. This is the beginning of architecture, of engineering, of design thinking. The same cognitive capabilities would have been essential for successful persistence hunting. To hunt by attrition, to wear down prey animals through hours of pursuit, required an understanding of animal behavior, of thermal limits, of landscape and water sources. The hunters had to be able to predict where the prey animal would go, to cut it off, to force it into positions where it would become exhausted. We have no evidence of language, though the potential for language was clearly developing. The brain regions that would eventually support language were being built through the practice of tool-making. But the actual spoken language, the ability to communicate in words and sentences and stories, may not have been present, or may have been only beginning to emerge. This raises a profound question. What were Homo erectus thinking about? If they had not yet developed language, at least not language in the form that modern humans experience it, then their thoughts would have been different from ours. They would have thought in images, in spatial relationships, in kinesthetic sensations. They would have understood the world through direct experience rather than through the mediation of language. They would have had knowledge, they would have had skills, they would have had emotions, but they would have experienced these things in ways that we can only partly imagine. And yet this does not make them less human. They were still human, still members of the genus Homo, still animated by the same basic drives and emotions that animate us. They felt hunger and thirst. They experienced fear and courage. They formed bonds with other members of their group. They felt grief when someone died. They experienced joy in successful hunts. They felt the pride of creating a well-made tool. They knew wonder at the world around them. They were, in all the ways that matter, human. As you rest deeper now, as the evening deepens toward night, allow your mind to contemplate this vast span of time. Nearly 2 million years, thousands and thousands of generations, countless individuals, each with their own life, their own experiences, their own joys and sorrows. The vast majority of them will never be known. We will never excavate their bones. We will never discover their tools. They will remain forever unknown, lost to time, existing only as part of the vast aggregate of Homo erectus, a species that existed for a time and then was replaced. And yet their lives mattered. They struggled, they survived, they reproduced, they passed on their genes and their knowledge to their descendants. They were real, they were here. The mystery of Homo erectus, of where they came from and where they went, of how they lived and what they thought and what they felt, remains incompletely solved. We have fragments, pieces of bone and stone, glimpses into lives lived so long ago that the scale of time becomes almost meaningless. 1 million years, 2 million years, the human mind struggles to comprehend such timescales, yet the tools they crafted with such care and precision have been buried in sediment, are being slowly discovered by archaeologists digging in ancient sites across 3 continents. The shelters where they lived, the caves, the rock shelters, the open-air camps, have been transformed. Some are now underwater, submerged by rising sea levels. Some are now barren desert. Some are now lush forest. The world that Homo erectus knew has been reshaped by the forces of geology and climate. Yet in our mind's eye, we can imagine them. We can picture them as they were. Real people, real individuals with bodies and minds and hearts that felt fear and love and hope. We can picture them as we lie here in the darkness preparing for sleep, connecting across the vast gulf of time with those ancient humans who also closed their eyes and slept, who also dreamed, who also awoke to face another day in a world both beautiful and harsh. We do not know what their dreams were like, what images and sensations played across their minds as they slept. But we can know that they slept, that they experienced something similar to what we experience, that the biology of sleep connects us across an almost unimaginable span of time. Consider what you share with them. You have the same basic body shape with some variations. You have long legs and shorter arms, a body adapted for bipedal running. You have eccrine sweat glands covering your skin, the same cooling system that allowed them to run for hours under the African sun. You have hands with opposable thumbs, capable of making and using tools. You have eyes that see the world in colour, that can perceive fine detail. You have ears that can hear sounds from nearly silent whispers to loud roars. You have a nose that can smell a vast array of scents. You have skin that can sense temperature and pressure and pain and pleasure. Your body is very much like their bodies, and your mind shares similarities too. You have the capacity for abstract thinking, for using symbols, for creating tools, for planning and coordinating with others. You have emotions, fear, anger, joy, sadness, love, compassion. You have the ability to recognize when others are suffering and to feel moved to help them. You have curiosity, the desire to know what lies beyond the horizon. You have the ability to imagine things that do not exist, to dream of possibilities. All of these mental capabilities likely had their origins in Homo erectus, or in the ancestors of Homo erectus. They were developing these capabilities, refining them, passing them on to their descendants, and eventually those descendants became us. And the mystery will still be there in the morning. The questions will remain unanswered, the story incomplete, the final chapter of Homo erectus still unwritten in the fossil record. We do not know exactly when they disappeared, or how, or why. We do not. It is a few scattered pages, fragments preserved by chance, by the geological processes that occasionally create conditions favourable for fossilization. For every individual whose bones were preserved and eventually discovered, countless millions lived and died, and their bodies returned to the earth and were completely lost. The story of Homo erectus that we can tell is only the barest outline, the vaguest sketch of a much richer and more complex reality. Sleep now, and let the ancient world fade. Let your breathing deepen, let your body relax into the support of whatever surface is holding you. Let the worries and concerns of the modern world begin to slip away from your consciousness. Let your dreams carry you back to those distant savannas, to caves lit by firelight, to the sight of ancient humans gathered around flames as the night grows deep. Imagine the warmth of the fire, the smell of smoke, the taste of roasted meat, the sounds of voices speaking in a language you cannot understand but whose tone and emotion you can sense. Imagine the stars above, the same stars that still shine today, unchanged by time, watching over the earth as they have for billions of years. Sleep, knowing that you carry within you the legacy of Homo erectus, that the genetic heritage of 2 million years of human existence flows through your veins and is expressed in the structure of your body and your brain. Sleep, knowing that you are part of a continuous lineage that has survived and adapted and persisted since time immemorial, that has faced extinction and survived, that has encountered new challenges and overcome them, that has spread across continents and learned to thrive in diverse environments. Sleep.